oxidation and reduction reaction. Oxidation, reduction of aldehydes and ketones. Out of which, first of all, we will see oxidation of aldehydes and ketones. As we earlier see that aldehydes are oxidized by suitable oxidizing agent like dilute nitric acid, then potassium permanganate, then acidified potassium dichromate oxidize aldehydes to corresponding carboxylic acid. RCHO is general aldehyde is oxidized by K2Cr2O7, which is acidic, or may say as in presence of dilute H2SO4, convert it into RCOOH. This is our carboxylic acid. This is acetaldehyde CH3CHO. It is called as a ethanol, or it is also known as a acetaldehyde is oxidized in presence of oxidizing agent like K2Cr2O7. Instead of K2Cr2O7, we can also take sodium dichromate in presence of dilute H2SO4, oxidize it into CH3COOH is our ethanoic acid. This is a oxidation of corresponding aldehyde to carboxylic acid in presence of mild oxidizing agent like dilute nitric acid, potassium permanganate, or acidified potassium or sodium dichromate. Ketones have strong C double bond or C bond is strong and therefore it resists to oxidation. But it can be also oxidized by using a strong oxidizing agent like chromium trioxide, CrO3, potassium permanganate, or nitric acid into a corresponding carboxylic acid. General example of ketone here is R, C, double bond O, R dash. When oxidized in presence of CrO3, in presence of chromic oxide, it convert into RCOOH. This is our ketone. This is a carboxylic acid, and also R dash COOH is formed. This is also called as a carboxylic acid. A mixture of carboxylic acid is a form having less number of carbon atoms than the starting ketone. Take a particular example of acetone will be given as like this: C double bond O CH3. This is our propanone, or this is also we called as a acetone. On oxidation, in presence of strong oxidizing agent chromium trioxide, gives ethanoic acid. Here is a CH3COOH. It gives a ethanoic acid. So this is about this is named as a ethanoic acid. Will be shown as like this. Here is a CH3, C double bond O, CH2, CH3. This is called as butane 2 1 On oxidation in presence of again chromic acid, it will give us a CH3 COOH and CH3 CH2 COOH is a form. This is known as a ethanoic acid, and this is our propanoic acid is a form. Here is 1, 2, 3, and here is only 1 and 2, and therefore it is known as ethanoic acid and it is known as a propanoic acid. So this is about the oxidation of aldehydes and ketones. Reduction of aldehyde and ketone is carried out by Clemmensen reduction and Wolff-Kirchner reduction. Reduction, aldehyde or ketone is reduced in presence of zinc amalgam and concentrated hydrochloric acid to corresponding alkane or carbonyl group is converted into methylene group. The reaction will be shown as like this. Carbonyl group of aldehyde or ketone is reduced by 4 nascent hydrogen atom reduced in presence of zinc amalgam in presence of concentrated hydrochloric acid gives it convert it into CH2. This is called as a methylene group plus water molecule is formed. If here is our aldehyde CH3, CH2, CHO, this is our propanol. On a reduction with nascent hydrogens liberated by zinc amalgam with concentrated hydrochloric acid, convert it into the CH3, CH2, CH3, that is a propane, a alkane. Convert it into a corresponding propane alkane, that is a propane. Here is another one example of ketone. Here is acetone or propanone is taken. This is called as a propanone, that is a acetone. It also reduces by nascent hydrogen in presence of same zinc amalgam and concentrated HCl. It convert it into a corresponding hydrocarbon, that is propane. So reduction is called as a Clemmensen reduction. Then samely, the aldehyde carbonyl group is also converted into a corresponding hydrocarbon by a Wolff-Kirchner reduction. Is again carbonyl group of this is a carbonyl group of aldehyde and ketone when react to hydrazine NH2 that is called as a hydrazine. It convert it into C double bond NH2 plus removal of water molecule is takes place. This is known as a hydrazone. This formed hydrazone are heat with NaOH or KOH in presence of soluble solvent like ethylene glycol. There is a CH2OH. This is called as ethylene glycol. Gives us a corresponding methylene group and liberation of nitrogen gas is takes place. A particular example, aldehyde CH3 CHO when react with hydrazine. This is called as a hydrazine. This is our ethanol. When reaction is takes place, it convert into CH3C double bond NH2 plus H2O is given out. This is called as a hydrazone. And this formed hydrazone here is a CH3C double bond NH2. When heat with potassium hydroxide in a solvent CH2OH CH2OH, that is ethylene glycol, formation of the CH3 CH3 is takes place plus nitrogen gas is evolved. This is called as a ethane. Same reaction is also takes place with aromatic ketone, ethyl phenyl ketone with C2H5 C double bond O C6H5. This is called as a ethyl phenyl ketone with hydrazine. This is our hydrazine. On reacting it with, it convert into this is known as a hydrazone, and this formed hydrazone on heating with a KOH in presence of ethylene glycol. This is ethylene glycol. Formation of the this is known as a N propyl. This group is called as a propyl group. N propyl benzene with liberation of nitrogen gas. So this is about the oxidation and reduction of aldehydes and ketones. Electrophilic substitution reaction as aldehydes and ketones shows electrophilic substitution reactions like nitration, sulfonation, and halogenation reaction. Aldehydic group and ketonic group containing a carbonyl group, and that carbonyl group is electron withdrawing group. This electron withdrawing group by inductive effect as well as resonance effect, they are stabilized, and therefore ortho and para positions are deactivated by the carbonyl group, and therefore it forms a meta substituted product. For example, when nitration of benzaldehyde is carried out in presence of concentrated sulfuric acid, it gives metanitrobenzaldehyde. The benzaldehyde CHO when hit with a HONO3, that is the concentrated nitric acid, when hit with a benzaldehyde in presence of concentrated sulfuric acid, this nitration is carried out. Formation of CHO, this is benzaldehyde at meta position, NO2 group is formed and OH goes with a H2O. Formation of a H2O molecule is takes place. This is called as, this is 1, 2, 3, 4, 5 and 6. This is called as a 3 nitrobenzaldehyde, or it is also known as a yam nitro benzaldehyde is formed. Samely, the halogenation and sulfonation of aromatic aldehyde and ketone is takes.
Reactions of aldehydes and ketones, chemical reactions of aldehydes and ketones. We have to see the chemical properties of carboxylic acid. First one is acidic character of carboxylic acid. As we see, the carboxylic group contain carbonyl group and a hydroxyl group. Out of these two in this carbonyl group, hydroxyl group dissociates a proton, forms a carboxylate ion. This carboxylate ion form a conjugate base, gives the acidic character to a carboxylic acid molecule, which shown as like this. Here is RCOOH. In water molecule, it is obviously reversible reaction. RCOO minus plus H3O plus is formed. This is called as a carboxylate ion, and formed by donating a proton to water molecule called as a protonium ion is takes place. This is responsible for the acidic property or acidic character of carboxylic acid. This carboxylate ion is stabilized by a two resonance structure which are shown as like this. Here is R C double bond O minus ion. This O minus ion can substitute its negative charge and form another one structure. Here is RC double bond O. A negative charge is on a double bonded oxygen atom. This is called as, this resonance structure is called as A and another one is called as B. Have a resonance hybrid structure, a stable resonance hybrid structure. Here is RC double bond. Instead of double bond, the double bond is distributed between two oxygen atoms, and it will stabilize it as like this. This is called as a resonance hybrid structure, and these two are a resonance structures of a carboxylic acid. Then we see the influence of electronic effect on acidity of carboxylic acid. As we say, the carboxylic acid will be represented as like this, RCOOH. All carboxylic acid have same pKa value, or they does not have a same pKa values. pKa values of the carboxylic acid is depend upon nature of R. R is an alkyl group, or it may be substituted by a electron withdrawing group or electron donating group. The pKa value of corresponding carboxylic acid is depend on this. This can be explained by a example of halocarboxylic acid. Here some halocarboxylic acids are given in which halogen atom is attached in a R. Halogen atom is an electronegative atom. This electronegative atom exert a electron withdrawing inductive effect, that is a negative inductive effect to the carboxylate ion, make it stable by a negative inductive effect of a halogen, make it more electronegative. As more electronegative halogen atom is attached to this, its pKa value is a least one. Least pK value becomes a stronger carboxylic acid. Will we explain in our book as like this. Here is a X attached to a CH2 group of a carbonyl group. Carboxylate ion will be shown as like this. Halogen atom exert a negative inductive effect towards itself, and this arise between a carbonyl carbon atom and a alkyl group present between them. It can be easily explained by a chart given in our book with different halogen atom. The different pK values are shown. More pK value becomes a weaker carboxylic acids, and lower pK value of carboxylic acid make it a stronger carboxylic acid is shown in our book. This acid is called as a 2-fluoroacetic acid or 2-fluoroethanic acid have the pK value 2.56. Chloroethanoic acid have a pK value 2.86. Bromoethanoic acid 2.90 pK value. Iodoethanoic acid have pK value 3.18, and only ethanoic acid have a pK value 4.76. As fluorine is a more electronegative than chlorine, than bromine, than iodine, and in acetic acid or ethanoic acid there is no halogen atom is present, and therefore haloacid which contain more electronegative atom fluorine have a lower pK value. That means its acidic strength is a higher one, decreases from fluorine to chlorine, chlorine to bromine, bromine to iodine, and then in a ethanoic acid it can be explained on this basis. Also, if same halo group are present, that is the mono halo carboxylic acid, dicarboxylic acid, tricarboxylic acid, the acidic strength or pK value is decreases, and therefore their acidic strength of carboxylic acid is increases with increase in number of halogen atom attached to a hydrocarbon in a carboxylic acid is also shown by another chart which are given in our book, that is the monochloroethanoic acid, dichloroethanoic acid, trichloroethanoic acid will be shown as like this. So this chart in which monochloroacetic acid or monochloroethanoic acid have pK value 2.86, which is a least acidic. Then the dichloroacetic acid or dichloroethanoic acid will be shown in this chart have a pK value 1.26. That means its pK value less than 2 monochloroacetic acid, and trichloroacetic acid have a very least 0.6 pK value. That means its acidic strength goes on gradually increasing, shown in this table which is in our book. Acidity of aromatic carboxylic acid. If we consider a aromatic acid, that is a benzoic acid, C double bond O OH, this is known as a aromatic acid, benzoic acid. As we see, the pKa value of this benzoic acid is 4.2. pKa value of this benzoic acid is 4.2, while there is of acetic acid is 4.6. The acidic property of a benzoic acid is a higher one than that of the acetic acid is explained on the basis of this carboxylic group is attached to a this carbon atom which is a sp2 hybridized. This sp2 hybridized carbon atom of aromatic ring exerts a electron withdrawing inductive effect, that is the negative inductive effect, stabilize the carboxylate base, increases its acidic property than that of the aliphatic carboxylic acid, that is acetic acid, in which carbon atom is sp3 hybridized, and therefore aromatic carboxylic acids are more acidic than the aliphatic carboxylic acid because of a electron withdrawing inductive effect of carboxylate ion which is attached to a sp2 hybridized carbon atom. Also, the electron withdrawing groups like the chloride ion, cyanide ion or nitrate ion, nitro group, increases the acidity of a corresponding carboxylic acid, while electron donating group like methyl group, hydroxyl group or ethoxy group or alkoxy group attached to a ring decreases the acidity of a corresponding carboxylic acid. So this is about the acidity of aromatic carboxylic acid.